Hi, my name is Joseph Caudill, and this is my final video project for ENME 489Y remote sensing with Dr. Mitchell at the University of Maryland. The goal of this project is to successfully sense an object on campus using a line laser, a camera, and Raspberry Pi, and then successfully model that object into a 3D point cloud to generate a mesh of that object from campus.
For my target, I chose to do the concrete bench right outside of EGR, the Glenn Martin Engineering Building on campus. Here you can see the location of the bench right outside the building, and here as well, it's right outside these doors. Here's a video of the bench. The main motivation for this bench was that it was something we all pass by every single day right outside the engineering building. And it was also easy to model since it was a light color and reflected the laser pretty well.
The sensor transmitter is the line laser that shoots the laser onto the target. The sensor receiver is the camera that takes a picture of the line laser on the target.
This image from NOAA shows LiDAR remote sensing. Remote sensing is obtaining information about a target at a distance without direct contact. Active sensing is using your own transmitter, such as sending a laser pulse, while passive is just measuring the light from the environment sources, such as the sun. LiDAR is light detection and ranging, and works by sending pulse signals of light and usually measures the time and waveform that returns to sense the environment. Computer vision is essentially machines sensing and seeing an environment. In this project, instead of measuring the waveform or time it takes for the laser to return, I measured the number of pixels the laser was from the center of the camera to generate distances. Here you can see my LiDAR setup. I have the line laser pointing at the wall, and then I have the battery pack, which is powering both the Arduino and the Raspberry Pi. The Arduino is powering the line laser, and then the camera is attached to the Raspberry Pi, and it's all on a 3D printed chassis, holding it all together. Next, I took the preliminary range data for both the laser pointer and the line laser. So I varied distances between 0.5 and 10 feet that were measured using a tape measure. And then I got the images that were outputted from OpenCV in Python for each of those distances, and then fit a model to them based on the number of pixels either the pointer or the line laser was from the center of the image. So here you can see the actual data from this. Using this curve, after adjusting the value specific to my LiDAR setup, I'll be able to generate distances based on where that line laser fell in the image that's generated. So here's the testing. I did an orange cone. So here you can see.
Hi, so we're back at our target. We're back here at this bench next to EGR. We've got our LiDAR set up. In this round, we're doing our data collection from all around the target. So we're doing multiple different perspectives. We're starting our perspective on this side at a 90-degree angle of our target of the bench. We're going to work our way around the bench and do a full 360 degrees. It's going to be a little bit difficult for a couple of reasons. Number one, I can't get fully around the bench on this side, so we'll have to move it a little bit closer, which will make it harder to get the full view of the bench in our LiDAR. Another reason is there's water in the ground, which makes the reflecting of the laser a little bit more difficult as far as the data processing will go. But yeah, so we're going to start over here. We got our angle set. Here's just an example. So we have our angle of 352 degrees. So we go ahead and hit enter. It processes that data. You can see the laser on the screen. We just keep doing that repetitively from the bottom of the target to the top to get a whole bunch of JPEG images of the target.
One of the biggest challenges in this for this target was light. It was the ambient light from the engineering building. Since the bench was located only a few feet away from the engineering building, where the lights are at all times, or where the lights are on at all times, made it difficult with all the light surrounding streetlights. So what I did to combat this is I put up a bunch of cardboard boxes around the windows and around the different light sources to try to block out that light, which seemed to help quite a bit. After the data acquisition of all the JPEG images from all 4 sides of my bench, that went into data processing of those images. So here's an example of one of the isometric views of the bench at 347 degrees. So I went in and changed the HSV values and was able to isolate only the red laser from the JPEG. Then using a combination of both the number of pixels that the laser was away from the center, as well as the data that I had from before to generate that distance and the angle of that image, or of that instance for that JPEG image. I'm then able to output a series of XYZ coordinate points, and I did this for all 20 images for each side, then generated a series of XYZ points for all 4 sides of the target. After generating the X, Y, and Z coordinate points for all 4 sides, I imported that text file into MATLAB. And here I translated and rotated all of the X, Y, and Z coordinate points for all 4 sides, moved them all into the same X, Y, and Z, and then filter out the data. So if the X, Y, or Z values were greater or less than a certain value, to make them 0. And then here's getting rid of all those 0 points, and then moving them into one single point cloud of all the X, Y, and Z points. So here's the unfiltered version of the points. And then after filtering it out using the same method I just described, here's the final bench that is created. So here's the 2 leg posts, and then here's the top of the concrete bench. Looking at the actual concrete bench versus my generated 3D point cloud, you can see they're very closely aligned. After creating the point cloud in MATLAB, I then took a text file of the X, Y, and Z points and put them into MeshLab. Here are all the points, the X, Y, Z points. I then created normals to those points, which you can see here. And then after creating those normals, I then created a mesh, a Poisson mesh from that. So here you can see here the two legs for the bench, and then here's the top of the slab of the bench. I filtered out some of the data. Yeah, here's the final bench.